update my OBS settings.
The recording's failing. I'm live. Oh, hi everyone who is here 2 minutes early. Well, 1 minute early now. We've been told that this day is annoying, or a slog that was put, so we'll see how this goes. We had a brief look at the puzzle. It looks a little bit tricky. I guess we'll see. Are you ready to
Almost. Okay. I'm pressing the record button again.
Alright.
Please don't fail again. Uh-oh, my OBS is like frozen up.
Oh dear.
Good times.
Good times.
I was connected for exactly like 10 seconds. Okay. This is... Oof. Okay, technical difficulties. Stand by, everyone.
Stand by. I need to get like a splash which says technical difficulties with marshmallow. Like I've got one which says top secret with marshmallow on it for if I'm like doing typing in passwords or anything like that, or doing file system stuff.
Amazing. Perfect. All right. Technical difficulties over. Stream on.
Nice.
Hey, everyone.
Hi, everyone. Okay, so this is 7-segment search. So you barely reach the safety of the cave when the whale smashes into the cave mouth, collapsing it. Sensors indicate another exit to this cave at a much greater depth, so you have no choice but to press on. As your submarine slowly makes its way through the cave system, you notice that the 4-digit 7-segment displays in your submarine are malfunctioning. They must have been damaged during the escape. You'll be in a lot of trouble without them, so you better figure out what's wrong. Each digit of a 7-segment display is rendered by turning on or off any of 7 segments named A through G. So here's 0. You can see it kind of makes a 0 pattern with all of these lines. Here's 1, 2, so on and so forth. So to render a 1, only segments C and F would be turned on. The rest would be off. To render a 7, only A, C, and F would be on. Okay. Problem is that the signals which control the segments have been mixed up on each display. The submarine is still trying to display numbers by producing output on signal wires A through G, but those wires are connected to segments randomly. So we don't know which... So, like, this says A, but this might be G or F or D. We don't know. These are mapped randomly. Yeah, this one looks a bit hard. Kind of thrashed in. We'll see. Worse, the wire segment connections are mixed up separately for each 4-digit display. So we have a number of different 4-digit displays, and they're all wired differently. But each of the digits within a display use the same connections. So we might know that only signal wires B and G are turned on. But that doesn't mean that segments B and G are turned on, because the mapping is random. The only digit that uses 2 segments is 1, which is this one, C and F. So we must know that B and G map to C and F. We don't know which one maps to which, but we know that at least B and G are C and F. Hey, Nick Toron, how's it going? For each display... Wait. Sorry, go ahead.
Hold on. Just to make sure I understand it. Because I thought I did before stream, but now I'm not so sure. So you're saying, like, if 2 wires are on, that corresponds to one of the numbers? We don't know which ones?
No. If 2 wires are on, right?
Yes.
It doesn't matter what those letters are. That is going to be the digit 1, because there's only a single number in here which has 2 wires.
Right. Okay, I see. Yes.
So if one of these, like, let's scroll down here. Yes. FG. In this case, FG for this line means 1. In this case, CG means 1.
I see.
In this case, ED means 1.
Yes.
So we need to map these onto these segments. Right. Where were we?
Yes. Understood.
For each display, you watch the changing signals for a while, make a note of all 10 unique signal patterns you see, and then write down a single 4-digit output value, which is our puzzle input. Using the signal patterns, you should be able to work out which pattern corresponds to which digit. For example, here's what you might see in a single entry in your notes. Entries wrapped here, anyway. So each entry consists of the 10 signal patterns. So these are 0 through 9 in a random order, I guess. Bar delimiter, and finally the 4-digit output value, which is this. Within an entry, the same wire segment connections are used, but you don't know what the connections actually are. The unique signal patterns correspond to the 10 different ways the submarine tries to render a digit using the current wire segment connections. So because 7 is the only digit that uses 3 segments, then DAB must be 7, and AB must be 1. So therefore you could work out that D, for example, maps to A here, because C and F are shared between 1 and 7, but A is not.
Yes.
So, using this information, you should be able to work out which combination of signal wires corresponds to each of the 10 digits. Then you can decode the 4-digit output value. Unfortunately, in the above example, all the digits in the output value use 5 segments and are more difficult to deduce. For now, focus on the easy digits. Okay, so we've got a big list of inputs. Because the digits 1, 4, 7, and 8 each use a unique number of segments, you should be able to tell which combinations of signals correspond to those digits, counting only digits in the output values, the part after the bar. In the above example, there are 26 instances of digits that use a unique number. Okay, so I think like we could go ahead and solve this. Do you want to first work out a mapping, like an algorithm for decoding the whole thing, because that's going to be part 2?
Oh, that's interesting. I feel like we might just be able to do the quick decoding of the first thing. That shouldn't be too hard, right? Like it's a count of like it's a character count.
Yeah.
So that should be like really quick, and then maybe we can like revisit that.
All right. Yeah, sure.
Regardless if I make it or not, or whoever like finishes first. At that point, we just jump in.
Yeah, sounds good.
Cool.
All right.
All right. I will mute my stream for real this time, not like yesterday. Good luck.
Cute. Okay, Yosh is gone. Let's get started. So, new day, new folder, day 08. New day, new file, and a new input. Okay. So let's just steal our setup stuff from previous day. Part 1, part 2, and day 8. Okay. R stream, F stream. And call part 1. Hey Walter, how's it going? Have any of you in chat done this puzzle? Because it seems like part 2 is gonna be a little bit difficult. We'll see. Okay, so we're gonna have to parse lines. So we're gonna use TL get lines. We're gonna be doing some splitting, so we'll get our split helper. Okay, so we're gonna do TL get lines, TL views, get lines or input, just new line. I think that's default anyway. Okay, for each line, we are going to, the TL get lines library is from my ranges library. I have my own ranges library, which has a bunch of helpers like getlines, chunk, Cartesian product, stride, things like that. Okay, so for each line, we are going to, I guess we can just split on space. Let's loop instead of doing all of this in a transform. for each line. Then we can do our split function. We're going to get std strings. And we're going to split on space. Okay, so now we've got a bunch of, let's call this just numbers, I don't know. So that should be all of these. Okay, so what we want is, oh, the pipe. The pipe is essentially a pipeline. It's taking all of the input from one thing, piping it into the next. It's like a Unix pipe. So let's call this inputs. Okay, so we've got our, hello Marshmallow. We've got our digits and we've got our output. So our digits is going to be inputs. We're going to take the first 10. Std views take 10. And we're going to want to parse this somehow. So the thing about 7-segment display here is, like, these are in different orders, maybe. Yes, like CG, EB is this, but the order doesn't matter. These are sets. Oh, sorry, the pipe in the input is just a separator. These are the 10 ways of representing digits for a given display, and this is the output that display is showing. So we're gonna take these. I think I can use bit sets for doing this, right? We've got like 7 digits, so each of these can be represented by a bit set of 7 bits. So let's write a 2-bit set for a given string view. Oops. String view. Keep mistyping include today. So to go from a given string view to a bit set, we're going to have a bit set of 7. And for each character in our string, we're going to set the bits of character minus A to true, and then return bits. Okay. So now we can do a std views transform to bit set to convert all of the 10 inputs to bit sets. And then we can do TL to std vector to convert this to a vector, for which I need hash include TL2, and I also need vector. Okay, so that should convert those digits. In order to get the outputs, I'm going to do essentially the same, but I'm going to std views drop 11 because that should drop all 10 of these and the pipe, and then give me these. Okay, so now I should have my digits, my outputs. Let's make a struct for this. Display std vector of std bit set of 7. Let's make this, what should we call this? Let's call this a digit. Oh no, sure. why not? The vector of digits is our representations. These are the ways that we can represent digits. And then we have another vector of digits, which is our outputs. Okay, so we could say make this into a parse display function, which takes a string view. Call line and returns a display with representations and outputs. Okay, so we should be able to do auto displays equals get our lines and pipe that to std views transform parse display, and let's collect this into a vector just to make our life a bit easier. Okay, that should be all our displays. So now part one should, I'm gonna have to do this for both parts, so just do parts displays, takes an iStream of our input, and just returns this. Okay. So our displays is parse displays for our input, and then our answer is just a sum of all of the outputs which have length 1, 4, 7, or 8. So std accumulate displays dot begin, displays dot end, loop overload displays, start at 0. For each display, we are going to return the number of outputs with 1, 2, 3, 4, 8. No. 1, 4, 7, 8 are the ones we're looking for. Okay, so we return if the we're going to count the ones which have either 2, 3, 4, or 8. Oh, that's what you're saying, Redwood Coast. Yes, thank you. 2, 3, yeah, 2, 3, 4, 7. Yes. So return std ranges count if display dot output. So for each of these, we're gonna count it if the bits dot, how do you get the number of bits set in a bit set? Is it count? Count. If bits dot count equals 2, 3, 4, or 7. Whoops. Ah. Oh, I accidentally set my keyboard back to QWERTY. If it's 2, 3, 4, or 7. Okay. I put that. Might work. Let's find out. Okay, so what we've done, oh, this is configuring and building. Parse the displays into a vector of these, which has a vector of bit sets for the representations and the outputs. Then we run over all of those. Oh, I'm gonna have to hash include numeric, aren't I? And I need, oops, correct quotes here. So then we run over those displays and we accumulate, sum up the counts of outputs which have 2, 3, 4, or 7 bit set. Okay, bit set is not a member of std. I should include bit set. Split, no matching, overload found, line 27. Does this take just a string? Okay, 56. Have I missed? Okay, so that's there. We need a semicolon here. Yeah, I think the parameter order is okay. Oh, I need to actually do the accumulation here. Turn sum plus. I could use my fold implementation, that might be a little bit cleaner, but let's just get this working for now. Okay, 0, well that's wrong. Let's stick a breakpoint here, see what our displays are. Wait, did I copy the input in? I didn't copy the input in. That would help, wouldn't it? I thought these were supposed to be on one line.
Alright, we got part 1.
Nice, good job. We're almost there, I think. I forgot to paste in the input, which always does, it does tend to help. Like,
yes.
Is 26 the correct answer for this? Yes. All right. Let me very quickly paste in my puzzle input. I think we're done. I just need to get the answer.
Amazing.
369. That seems a little low. I don't know.
Did I have? No, I had a similar one.
Yeah. Okay. Yeah, we're done.
Hey, perfect.
Okay. So that's part 1. Part 2. This is gonna be horrible. I can just tell. Alright.
Yeah, we had like friends warn us about this puzzle. Probably not about the first part.
Through a little deduction, you should now be able to determine the remaining digits. Consider again the first example. After some careful analysis, the mapping between signal wires and segments only makes sense in the following configuration. And that's the configuration. Okay. And then you can do similar thing. And then them all up. Okay, so we need to determine all of the wire segment connections, decode the 4-digit output values. What do you get if you add up all the output values? Okay, so, right, let's work out the algorithm for decoding.
Wait, I feel like you're two steps ahead of me.
Sorry, it's exactly what you would imagine it is. We need to decode the mapping between the between each line, and decode the output and digit, and then add them all together.
Wait. How does that work? How do we know that CDFBE is 5?
Through deduction.
Deduction.
Yeah.
What?
So that's
Are we
what
Sherlock Holmes now?
Right. I'm gonna start writing some comments. Right. So we're given 1, 4, 7, and 8. Right. We can work those out just through how many elements are, how many sides they have. Okay.
Yes.
So the question is, how do we deduce the other ones from that? So like, for instance, you can deduce 9 because it has 1, 2, 3, 4, 5, 6 side set and contains the same configuration as 4. So if a given string has 6 character set and has the characters from 4 as a subset, then that's going to be 9.
I see now.
So count is 6 and contains 4 implies 9. Okay, what else have we got?
So the left hand side contains the mapping, and then the right hand side contains the value that we want to the values that we want to decode with that mapping.
Yes.
I see now.
And
then the puzzle question is, what do you get if you add up all the output values? So we do the mapping every time. All right. Oh, that's fun.
I think we should maybe work out the algorithm for it together, and then we can actually split off and implement it ourselves.
Yes.
Okay, so we can work out 9. So we then let me write down the ones which we have and the ones which we do not have. We do not have 1, 2, 3, 5, or 6. Okay, so we can deduce 3 from having a count of 5 and a subset of the characters in 1, because 2 and 5 are the only other ones with 5 lines set, and neither of them contain 1 as a subset. So count equals 5.
Which one was which?
And contains 1 is 3.
1, 2, 3, 4, 5. Count 5.
Okay, from there, we can deduce. Oh, sorry, I missed 0 from here. From there, we can deduce 0 by. It has 6 sides set. It has 1 as a subset, and we've already worked out 9, so we can eliminate 9, and 6 is the only other one with 6 sides set, and it doesn't have 1 as a subset. So after doing that, count equals 6 and contains 1 implies 0.
Yes.
From there, count equals 6 implies 6 because it's the only one left. So then we just have 2 and 5 left. which we can determine by, we know 6. 5 is a subset of 6. So then
5
count
has 5
equals
sides.
5 and is contained in 6 implies 5. And
Yes.
then count equals 5 implies 2 by process of elimination.
Oh, I see. Wait, so both 3, 5, and 2 have 5 sides?
Yes.
Okay.
So count equals 2 implies 1. Count equals 3 implies 7. Count equals 4
I'm missing 9.
implies 4. Count equals 7 implies 8. Okay.
And count equals 9?
Pardon?
Or, sorry, number 9?
Number
How do you get
9
that
you
one?
get right at the start from deducing that if it has a count of 6 and it contains the same wires as 4.
Oh, right. Same wires as 4? Wait, 4 is a subset of 9.
Yes, exactly.
Given check if 4 is a subset. All right, interesting.
Yep.
So it seems like what we need to do is we might need to do like multiple passes, where first we get like the given numbers, and then we can deduce 9. We can deduce, because some of them require like the extra step of like the intermediate deductions. Specifically 2 requires that we understand like 3 and 5 first.
Yeah. So I think we start off with working out which ones are 1, 7, 4, and 8, and then you loop through all of the remaining ones and deduce 9 and 3, and then you loop
Yes.
through the remaining ones and deduce 0 and 5. No, sorry, you can't do 5 yet. You have to do loop through them again, deduce 0, loop through them, deduce 6, loop through them, deduce 5, and then you're left off with 2.
Yes. Yes.
All right, you ready?
Okay. Yeah.
All right.
Yes.
Let's go.
Good luck.
Okay, so I'm gonna have a mapping, which is just an array of digits for a given display. So we have all of our displays. Oops. So we're given all our displays, and then we're going to deduce them. Maybe we'll make this a member function of display. Okay, so we start off with our representations for auto digit, well, let's just call it D, in representations. Should have picked a shorter name for that. We can just switch on d.count. If the count is 2, then our mapping of 1 is going to be set to D. Break. If it's 3, 4, 7, then if it's 3, our mapping of 7 is going to be D. Here, it's going to be 4. Here, it's going to be 8. Okay, that deals with those. Then we loop through them again. And our default case, we just break. Loop them again. If d.count equals 6 and contains d4, can implement contains in a sec, then mapping of 9 is going to be d, else if d.count equals 5 and contains d1, then our mapping from 3 equals d, then do the same. If count equals 6 and contains 1, then we've worked out 0. Then that deals with that case. If the count is 6, then we've worked out 6. And if we're also going to have to erase at each step, so our deductions work. The count is 5 and contains is contained in 6 if I am getting myself confused here. If contains, let me write contains since I'm getting a little bit confused. Auto contains if std bit set 7. Okay, right. We take 2 bit sets. Bit set 7 b, and we return. So if a contains b, then doing a bitwise ANDed with b should equal b. So this is, we need to change all of these. To index our mapping. Okay, and then here we're checking if 6 contains d. And then our okay, and we need to make sure to erase at every level as well. So we can do std erase from d dot, from representations. This can be annoying. Oh, I got Marshmallow here. Say hi to chat, Marshmallow. Hello. He is a little teddy bear. Okay, so I want to erase mapping 1. I want to erase, all of these mappings from the vector. This is not very clean or efficient, but this will do. And then here I want to erase this from representations. Here I want to, 9, 3. Here I want to erase 0, and here 6, and what was that supposed to be? 5, right? And then we should be left with one last one. We're mapping 2 equals representations, the only one left. Okay, that should be our mappings. So we're going to parse all of the displays for autoref display in displays. We're going to decode them. Or did I call this deduce? Decode's better. And then we're going to get our output. What am I missing here? Ah, there we go. Auto output equals. Okay, so for each number in the output, we do a reverse lookup in our map. Does std array have a find? No. Okay, we'll just use std find. Auto. Let's do a reverse lookup function. Decode output for a given digit. Return std find in our mapping the digit d, and return the difference between that iterator and mapping. Dub again. I'll do our reverse lookup. So we do, and then we need to convert that to a decimal number. So we can do what do we call this? Output. Call this get output. Hey, thanks for the raid, Mercenary Mage. Okay, so we're gonna get our output. We're going to pipe our output to std_views transform, decode output. This will give us each individual digit looked up. Then we need to convert this to decimal. And thanks to follow, Psychazker. We need to convert this to decimal, which is reduction. We can use TL fold, which I implemented a couple days ago. In here, this is just, do they even call this TL fold, or is it just regular fold? Yeah, TL fold. This is just a left fold implementation. Where am I? Okay. So I'm gonna take my decoded digits and I'm gonna fold them by decoded digits. Our initial value is going to be 0, and on each iteration we're going to take our accumulator and our new number and return accumulator multiplied by 10 plus n. That should convert our number to that should convert our 4 digits into a decimal number, which we can then return. Okay, and then our final thing of part 2 is to do another fold on our displays, tail fold, displays, our initial value is 0, and I forget, is this a unary or binary operation? That's binary operation. Okay. Our accumulator and our display, and we're going to return accumulator plus display.get output. And in theory, that should give us our answer. Whether this will work or not, I have no idea. What's going on here? Line number 93. Output is a vector of digits. Decode output takes a digit. Oh, I need to pass it this. Oh, that's not going to work because it's a member function. Just stick it here. Oh no, I do need a... Okay, I'll just pass a lambda, which captures this and takes digit and returns decode output for that digit. Did I just completely get rid of my function? Yes, I did. Okay, where was it? Just here. Okay. Well, that ran part 1 again, but it compiled, which is good. Let's see what we get. Okay, well that's a number. I have no idea if it's correct or not. Let's stick it in, and then we can enter our debugging phase when this... Wow, okay. It worked first time. Incredible. Alright. Tell Yosh we're done. Hey Yosh, we're done.
Oh, that's quick. Nice. Yeah, we're on our way. I feel, yeah, we're just struggling with like what does or doesn't have a particular trade bound. So it's a bit of Rust specific issues, but shall screen share? Do you want to join in?
Yeah, go ahead.
Yay. Screen. Share.
Yeah, Rob would saying we're thorough in planning before coding it. I think that's what made this easier. Like, we worked out the algorithm, and then translating that to code was not too difficult after we got it working.
Yes.
Let's put your screen on. Okay. Your screen is now on my screen.
It's good to have screens. All right. So what we have is we're still like on the left hand side doing the mappings into we are wait, hold on, where are we? Oh yeah, I was just doing the mappings here from going from left hand side where we're doing the known inputs first and putting them, I was trying to put them into a hash map of hash sets of U8s so we have like a nice little mapping, but that seems like it might not be possible because hash set doesn't implement like a particular trait.
I just had an array of 10.
Oh, that makes sense.
Because you've got 10.
Oh my god.
So you just use the number as the index into the array.
Yeah, okay, there we go. And this is why it's helpful to have someone else around. I think we're going to do a hash set of string and then 10, right? Yeah. We can do... wait, hold on, what's going on? I forgot how to initialize arrays.
So
Hold on.
Wait,
Yes.
you've got a hash set of strings. Why
Yeah,
is
well-
why is that hash set of strings? Don't you want a hash set of characters?
We totally do.
Bytes. I mean, I did it with a bit set.
Oh, I see.
Because I just need 7 bits. Each one's either 1 or 0. That indicates whether a given line is activated.
Oh, I see.
One sec.
Yeah, we almost went there. I figure what I do with the hash set is just how to say that. Yeah, and like the bit field stuff is like more efficient, but hash set I figured would be easier because we just have all the characters and just are like, hey, there's this bag of characters, and it has an intersect method, so we can like compare one bag to the other bag and be like, is this a subset of? Yeah.
But I just did that with you can bitwise AND them, and if the bitwise AND returns the same thing that you gave it, then it's an intersection. So, but yeah.
Remember my day 3 when I tried to do like bit bit splittling? We're not doing that again.
Anyway, yeah, you
yes.
hash set of strings, I guess, works fine.
Map to equals set. Is that it?
Yeah.
Found mutable reference. Oh yeah, we need to do intuiter like that, and then otherwise we remainder equals vec. We're gonna do this is super inefficient, but push set. Yes.
Ah, okay. Yeah, I did the opposite. I erased everything from our it's the equivalent.
I found that to be like somewhat like tricky in like Rust to do because you're like mutating a vec like inline and the borrow checkers and like tuples about that.
Right. Yeah.
So I was like, let me just like.
I just did it after the fact. It looks horrible, but it works.
What's going wrong here? Something is complaining about something else. Marker copy. Wait, what are we trying to move? Why? Because the repeated elements will be copied. You know what? We're just going to make this a vec. A vec of option that. Sometimes we want to be clever and efficient, and sometimes we just want to be done with half of the code in time.
You need to be careful though, because if you want your vector to be of size 10, right? And you don't want to be pushing elements into the front. You want to size it ahead of time.
Don't I? Yeah, you're entirely right. Yes, you are right. Oh no. Why are you right? Stop it, Si. Non 10. Does that work? Okay, that seems to work. Okay. We're probably non-initializing the vector. We're indexing correctly. We are pushing the right values in the right spots. Okay, that works. So now we have a remainder. So now we're at parsing 5 is a subset of 6.
You want to do 1, 4, 7, 8 first, right?
Yeah. Oh, hold on. I thought we were done with that. Count 4. Is this right?
yeah, that's
Yeah.
that's what you want. Yeah.
2,
And
4, 3,
4 should go to 4.
7. Yes. 4, 7, 8. Right.
Looks good. Yep.
Yes. And now we can like loop over our remainder. Let's try this one more time. Our inner function is a bit different. Now what we need to do is if set dot sub, what is it? Let's I'm gonna look at the hash map methods real quick, or hash set. Hash set. Sub is subset. Hey, there we go. Is subset. For set in remainder. Wait, why is our map a remainder? Oh, we can just like unwrap there. Can we? No, that's our map. But our, what's the type of our remainder? Vec of hash set. Vec of unknown? Oh. Remainder 2. That explains it. Yeah, I know. It's great.
Remainder 2. This is where we keep the good code.
Fine. Head equals remainder. Fine. Head. Seta is subset of map subset of 6. Count 5 is subset of 6, but we don't have 6 yet, do we? Does that need to go there?
So I did. So after doing 1, 7, 4, and 8, I did 9 and 3.
Oh, you did 9 and 3. Sure. Count 6. Check if 4 is a subset.
Yeah.
So what we'll do now is if set.len equals 6, and then set is subset of map
4.
4. Wait, is 4 a subset of 9? Or is 9 a subset of 4? 4 is a subset of 9.
Yeah. So you want the other way around. Map 4 is subset of
is
set.
superset. Hell yeah. Inverse. Then we can set number 9.
Yep.
Equals some set. And hash set. Found in what's going on? Oh, we need to like that. Found and option. As ref dot unwrap. Is that right? That is right. Cannot index a value of type hash sets string. Cargo check. Let's take a look. What's going on? Unused imports. Oh, set. Hold on. We don't need to do
9.
that. Yeah, exactly.
Yeah.
Remainder is unhappy. Well, we can comment it out. All right, there we go. Else if.
Yeah. Then you want to check for 3.
Push set. So that's the final case. Okay, so our 3 requires has 5 segments, is a subset of 1.
Yeah.
set
No, it is one a subset of 3.
Oh, one's a subset of.
Yeah.
Check if 1. Or we can say superset of haha 1. Else len equals
5
and
set supersets map 1
superset map 1. This is not nice. Unwrap. We're doing the right invocations to get a reference through an option, and it's not ideal. Set line 5, and then we do map 3 equals some set. Count 6. It seems like we should be able to do 0 now, or is that in the next pass?
I did. Yes, I did 0 next. Yeah.
Yeah. Okay, so 0 is count of 6.
No. You need to do 0 in the next pass. Yeah.
Next pass.
Yeah, because you need to know 9. You need to have eliminated 9 first.
Oh, okay.
At least the way I did it. Like, I'm sure there's ways you could do it, but
who cares? We care about getting to solution.
I think that this solution is better than brute force, so I'm happy with it.
That's true, and I'm sure we could do it with fewer allocations in my case, but you know, okay. So our mapping is for 3, count 5, superset of 1. No, we already have 3. Hold on. We want 0, count 6, subset of 1, right? 0 is a subset of 1?
0
superset of 1. Yes. Superset of 1. Count 6 is superset of 1, and then map 0 is that. And then we can do count 6 in the next one.
Yep.
Which is also count 6. Oh, that's the last remaining 6 then?
Yeah, it's the last remaining 6. Then you can do 5.
Is that just 5 is a subset of 6?
Yeah, count is 5. Well, you don't even need to check count is 5 anymore because the only 2 left both have count is 5.
Oh, yeah, you're right.
Not they'll make a difference.
Is 5 a subset? Subset of 6. 5 is a subset of 6.
Yeah.
Okay. Set is sub. Actually, I'm gonna just copy this over.
Yeah.
I don't want to keep typing stuff. Typing is done. Subset. And of 6. Oh, 5.
Yeah, and then
the last one is
you should have 1 element left in your remainder, which should go into map 2.
Well, we can just do this, right?
Yep. I can do it in mine as well. It would eliminate a step.
Because do we know that if it's not a subset of 6, then we can just push it? That is correct, right? Yeah, okay. And that means we have our mappings. Cool. That's good. And then now we can do our pass where we do the final You did this like really quickly, by the way. I'm surprised.
My whole solution's like 140 lines of code.
Yeah, we're about to hit that. Variable does not need to be mutable. Interesting. Remove this mute. Remove this mute. I'm just gonna remove all the warnings real quick. Unused imports. Alright. Sure. There we go.
Alright,
Okay,
so
mostly gone.
that should give you your mapping, and now you just need to go through your outputs, convert those, do a reverse lookup in the mappings, and then convert them to decimal numbers.
Yes.
And that's them together.
Yes. Okay. Reverse lookup. How do we do this? We have our outputs, so everything on the right hand side of the thing. It seems like we can convert them back to like hash sets. Like that. Wait, is that right? Outputs. Vec. Wait, do we already have our outputs parsed? Oh, it seems like we already do. My bad. Yeah, so we have a vac of hash set already. Reverse lookup. How do we do that? We have our map of numbers. So I believe we can do outputs dot map set. So we have our individual sets.
Mm-hmm.
And then I think we should be able to like do it equals for lookup in